In this video, we're going to take a look at section 6.5 on rationalizing the denominator. The phrase rationalizing the denominator means to clear the denominator of any radicals. So there are different classes of numbers, different categories of numbers. One category of numbers is the whole numbers. Beyond that, we have the integers, which are whole numbers that could either be positive or negative. And then beyond that, we have the rational numbers, which are numbers that can be written as fractions, like 1/2, 2/3, and also whole numbers are included in that as well, like 5/1, which is 5, right? You can write 5 as a fraction, 5/1, that's a rational number. The thing about writing it as a fraction is it has to be a whole number on top and a whole number on the bottom. So that's what makes it a rational number. But then you have numbers that cannot be written as a fraction in that way, such as square root of 2. That is a number that cannot be written as a fraction with one whole number on top and one whole number on the bottom. These numbers are called irrational numbers. You can recognize them because their decimal form is an infinite decimal expansion that doesn't repeat a pattern. So like square root of 2 is 1.41 ... It just has an infinite amount of numbers, in fact, not just a bunch, but an infinite amount of decimal places where there's no pattern that just gets repeated over and over and over. Pi is an example of this, right? 3.1415. That's an irrational number as well. We don't want irrational numbers in our denominators. That's the standard way of writing a number is to not have irrational numbers in the denominator. And so whenever we're given a fraction that does have an irrational number, like a square root of 2 or cube root of 5 or pi even, we want to rationalize that denominator. We want to turn it into a rational number, preferably a whole number, right? So we want to get rid of the radical, make it into a whole number so it's a rational number. That's what rationalizing the denominator means. This is done by multiplying the necessary expression to the denominator to make the radical cancel out. Unfortunately, you cannot use exponents to cancel out these radicals. So you can't just say square the square root to make it cancel out. That's not a valid way of changing a fraction. You have to do it through multiplication. So we'll have to figure out what do we multiply to this radical to make the radicals all go away in the denominator. And whatever we multiply to the denominator, we have to also multiply to the numerator to balance the fraction out. So let's take a look at a couple of examples. So here we have square root of 15 over 2. Now, on first glance, you might think, oh, this is actually fine. It's just a 2 in the denominator. But really, it's a square root of 2 in the denominator. So we learned about this back in, I think, section 6.3, that this square root applies to both the top and the bottom of this fraction. And if you write it that way, it becomes clear we have an irrational denominator, right? We have square root of 2 in the denominator. We don't want a square root to be there. What we just learned in the previous section, 6.4, it's a shortcut that I told you guys about, is that when a square root gets multiplied to itself, the square root goes away. And that's exactly what we want to have happen here. So what we'll do to get rid of this square root on the 2 is to multiply by another square root of 2. And the shortcut is that when you multiply a square root to itself, the square root goes away, and we just get 2 as our answer. All right. Again, the background for that is when you multiply square root of 2 times the square root of 2, that really is equal to the square root of 4. But the square root of 4 is going to simplify to 2. So it's a shortcut that we have. When you multiply a square root to itself, the square root disappears. You just get the number that's inside the radical. All right. Now, if I multiply square root to the denominator, I have to multiply the same thing to the numerator to balance the fraction out. And so on top, we're going to get square root of 15 times the square root of 2, which is going to give me the square root of 30. And so this is how we rationalize the denominator. So now my denominator is a whole number instead of being a radical. And that's what we want to accomplish. We'll do the same thing for this example. We have 25 square root of 7 over 7 square root of 5. We're going to multiply to the denominator something to cancel out the square root. We don't really care about the 7. And so we don't have to worry about what do I multiply to the 7 to make whatever happen. It's not an issue for us. It's just the square root of 5 that's the issue. So all I need to do is multiply by another square root of 5. That will cancel out that square root of 5. So you might be thinking I'm talking about it in a weird way, but let me just explain why. Because what I'll see students do on the test, it's not completely wrong, but it's just more work than it needs to be. I'll get a lot of students that multiply by another square root. Sorry, I'm saying the wrong thing. They multiply by another 7 square root of 5. So they include the 7 here when they multiply to this. And I understand why they might think to do that, because what we're doing here is multiplying by a copy of itself, right? So for square roots, you multiply it by a copy of itself, the square root goes away. So you're thinking the same thing here. 7 square root of 5, I multiply it by a copy of itself, the square root will go away. But this 7 here is unnecessary. It does nothing to help us get rid of this square root of 5. All it's doing is getting in the way. It's just going to make numbers bigger than they have to be, and you're going to have to reduce it afterwards you're just going to end up canceling that 7 back out at some point, basically. And so it just makes the problem more work than it needs to be. So if you do that, it's possible to still recover from that and get the right answer, but it's not necessary. It's an unnecessary number to multiply by. Just a square root of 5 is going to get the job done. So that's what I'm going to suggest here. Only multiply by a square root of 5. And so we're going to get 7 square root of 5 times square root of 5. You multiply together what goes together. The square root of 5 times the square root of 5 multiply together to give me 5. Right, that's the shortcut. When you multiply a square root to itself, you just get the number that's inside the square root. And then we'll have 7 times 5, which is going to be 35. And now this is a rational denominator. So we have rationalized the denominator by multiplying just by square root of 5. We don't have to worry about having another 7 there. So I hope that made sense. If we multiply square root of 5 to the bottom, we got to multiply the same thing to the top. So we're going to get 25 square root of 7 times the square root of 5. Multiply together what goes together. The 25 just copies over. Square root of 7 times the square root of 5 multiply together to give me the square root of 35. Then we want to try to reduce. We should have maybe tried to reduce over here. I didn't mention it because nothing here reduces. So be careful. Numbers inside the square root cannot cancel out with numbers outside the square root. This 2 is not inside of that square root, so it doesn't cancel out with the 30. So that fraction doesn't reduce. Same thing is true here. This 35 does not cancel out with this 35 because one's inside the square root, one's outside the square root. But this 25 is outside the square root. This 35 is outside the square root. Those can be reduced because they're both divisible by 5. So we can reduce those two numbers, and we will get 5 square root of 35 on top and 7 on the bottom. And that'll be my final answer. All right, let's take a look at another example. All right, here we want to rationalize the denominator, but this time it's not a square root, it's a cube root. Unfortunately, that shortcut we were just using in the last couple of examples does not work here. When you multiply a square root to itself, the square root goes away. But that is not true for a cube root. So what I will see students do on the test, sorry, that was a horrible line. What I'll see students do on the test here is they will multiply this by a copy of itself as well. They'll say, oh, I'll multiply this by a cube root of 2c. But that doesn't cancel out the cube root. The cube root does not go away. When you multiply these two together, you get the cube root of 2 times 2, which is 4, and c times c, which will be c squared, and neither of these cancel out that cube root. So the cube root's still there. It didn't get canceled out. So that shortcut does not work with cube roots. You can't just multiply a cube root by a copy of itself. That never works. You have to be a little more, you have to do a little more planning to make it work out. So remember, a cube root cancels out powers of 3. So the way I approach this, it might be a little different than you'll see on Math Excel or that you might hear from a tutor or from another student, is I look at the exponents. Cube roots will cancel out things that are raised to the third power. So I try to get everything raised to the third power, right? This is 2 to the first power. This is c to the first power. So how many more powers of 2 do I need to get 3 so it cancels out with the cube root? I need 2 more, right? 2 squared. That way when this 2 gets multiplied to this 2, I'll have 3 powers of 2 altogether. Then that power of 3 will help me cancel out the cube root. I have to do the same thing with c, and it's going to be the same answer, right? I already have 1 power of c. I need 2 more to get 3 altogether. And then with 3 powers of c, I can cancel out that cube root, right? And so that's what I focus on. Sorry, I'm doing a really bad job of drawing these fractions here. Okay, let's try that again. All right, so now I will multiply these together. So we did something different this time. Multiply them into a single cube root. 2 times 2 squared will give me 2 to the 3rd power, which is 8, but I like to just keep it as an exponent. C times c squared will give me c to the 3rd power. And now I can apply that cube root to each of these, and the cube root cancels out the power of 3 each time. So what's going to happen here is, what I'm doing is splitting it up, applying it to each one separately. Right, so like this. And now the cube root cancels out the power of 3, and I just get 2 from this first one. And here the cube root cancels out the power of 3, and I'll just get c. And now the cube root is gone. It's the same approach for fourth roots, right? A fourth root will cancel out powers of 4. So my goal is to get everything inside the radical raised to the 4th power, then the fourth root would go away, right? Fifth roots cancel out with powers of 5. So if I get everything raised to the 5th power, the 5th root will go away. So that's the way I approach these radicals when they're not square roots. If it's a square root, I multiply it to itself. If it's a cube root or higher, I get everything raised to that power. That's what makes it go away. If I multiply this to the bottom, I got to multiply the same thing to the top. So I have to multiply cube root of 2 squared c squared to the top. And so when I multiply those together, I'll get the cube root. 2 squared is 4. 4 times 7 is going to give me 28. And then I'll have a times c squared. So a and c squared just get multiplied together inside of that single radical. And then we maybe try to simplify this cube root, but there's no way to split up 28 for it to simplify, right? For cube roots, we want 8, we want 27, we want 64. None of those numbers come out of 28. And then the variables don't have enough powers to cancel out with a cube root. So there's nothing to split up here to make anything simplify. So we just copy it over. We'll have cube root of 28ac squared. And again, these don't reduce because this is outside the radical, that's inside the radical, so they cannot cancel each other out. So the correct answer is what you see on the screen. All right, let's try another one. Let's see. Okay, so we're back to this one's a square root. This one's a little bit, so let me just explain what my hesitation is here. This square root applies to the top and bottom, right? So we get square root of 5x over square root of 18. So we do need to rationalize this denominator, just like the previous problems. Square root of 18, if you could keep the same approach we were using before. It's a square root, so you can multiply it by a copy of itself. That will make the square root go away, but it is not the most optimal way of doing it, because square root of 18 actually can be simplified. And so you're going to get kind of a big mess in the numerator that has to be simplified by splitting it into a good pile, bad pile, and then it'll be reducible after that. So it ends up being a few extra steps if this is how you do it. It works, but it's just a little bit more effort. What you probably want to do in this case is simplify the square root first before you decide what you should multiply by. So 18 can be split up as 9 times 2. And we can apply the square root to each of those separately. And so this problem becomes, let's see if I have room to write it down here. We'll have square root of 5x over, this will be 3 square root of 2, right? So square root of 9 gives me the 3, square root of 2 copies down. And now, what should I multiply by to make this square root go away? I want to cancel out that square root, so I multiply it by a copy of itself. I multiply by another square root of 2. And again, we don't have to worry about the 3. That's not an issue here. We can just ignore it for now and focus on what do I need just to make this square root go away. I need to multiply by another square root of 2. If I multiply that to the bottom, I have to multiply the same thing to the top. So on the bottom, what I'm going to get is 3 square root of 2 times square root of 2. When you multiply these square roots together, square root of 2 times the square root of 2 is just 2. And then 3 times 2 is going to give me 6. I'm sorry, it's like, it makes me think of like Willy Wonka or something. It's just like, it's kind of crazy all over the place. So I apologize for that. Okay, so 3 times 2, which gives me 6. I go back to the numerator, multiply these together into a single square root. We'll have 5 times 2, which will be 10. And the x just gets copied over. Nothing from that simplifies, so we're just going to copy it over to the answer, and that'll be my final answer. So we get square root of 10x over 6, which is the same thing you should get if you do it this way, but it's just going to be a longer route, right? Because on the bottom, you're going to get 18. Up here, you get square root of 18, which will be square root of 90x. That has to be simplified. It'll simplify as 3 square root of 10x when you simplify it, and then you reduce the 3 and the 18 and you get 6. So eventually you get there. So what I'm trying to say is on the exam, try to look for, to see if this could be simplified, and then rationalize the denominator based on that. If you can't see how to simplify it, then you can always fall back on multiplying the square root by a copy of itself. Even if it's not the most optimal way, you will still get to the correct answer if you are persistent enough. All right, so let's look at, I think this is my last example of single radical. So let's go ahead and take a look at this. First, we will apply the cube root to the top and the bottom of this fraction. All right, and so that's what we get. Then we want to rationalize the denominator, which means now this time we kind of, you could, now I'm going to sound like a hypocrite because here I was like, simplify this first before you do anything. You could simplify this with the variable x to the 11th power by splitting that up as x to the 9th power times x squared. You can get something outside the radical when you do that. But with variables, I don't think it really saves you any time to simplify the variables. Numbers, yes. If the numbers can be simplified inside the radical, you should do that. It definitely is a time saver and makes the problem easier to do. Variables, it doesn't really help that much. So I'm just going to leave it the way it is. All right, so let's get rid of all that. And my goal here is to get everything inside of this radical to be something with an exponent that will simplify nicely with a cube root. And like I said earlier, cube roots cancel out powers of 3. So that's going to be my goal here. For the 2, I want to get that to the 3rd power, so it cancels out with the cube root. And for the y, my goal here is to get this to be to the 3rd power, so it cancels out with the cube root. But for the x, we already overshot 3. So the next best thing is to get an exponent here that can be divided by 3, because that's how it will simplify. As long as this exponent can be divided by 3, it simplifies nicely. And if it simplifies nicely, the cube root just goes away. And so my goal here is actually going to be to make this a 12. Right? It's already at 11. If I can get it up to 12, 12 can be divided by 3 and it'll simplify nicely. Right? So get exponents in here that will simplify nicely with the cube root. So we already have 1 power of 2. I'm going to need 2 more powers of 2 to give me 3 altogether. That simplifies nicely with the cube root. I need 1 more power of x. I already have 11. If I get 1 more, I will have 12. And then that will simplify nicely with the cube root. And then with y squared, I already have 2 powers of y. I just need 1 more power of y. That will give me 3 altogether, which simplifies nicely with the cube root. So this is what I'm going to multiply by. It has to be inside of a cube root for these to get multiplied together. And so what we're going to end up with is the 2's multiply together to give me 2 to the 3rd power. The x's multiply together to give me x to the 12th power. The y's multiply together to give me y to the 3rd power. And oh, that was not good. Probably should have drew this first instead of afterwards. Let's see, okay. And we're taking the cube root of that. And so when we simplify the cube root of 2 to the 3rd power, the cube root cancels out the power of 3 and we just get 2. When the cube root applies to the x, we divide. 12 divided by 3 is going to give me x to the 4th power. And then here for the y, the cube root cancels out the power of 3 and we just get y. And so we've rationalized the denominator because there's no radical left in the denominator at this point. Because that works out, so I like to do that first, make sure the denominator is actually going to work out with no radicals. Once I've confirmed that this is what I need for this to work out, I go back and do the same thing to the top. So cube root, I want to write the 2 squared as 4. It's the same thing. I'm multiplying the same thing to the top, just as a 4 instead. X to the 1st power, y to the 1st power. Multiply these together. We're going to get the cube root of 5 times 4, which is 20, and then the x and y just copy down. And this doesn't simplify, right? For cube roots, we want 8, 27, 64, or 125. You can't get any of those numbers out of 20. And the x and the y don't have enough powers to simplify with the cube root. So we're just going to copy it down. So we'll get cube root of 20xy here. All right, and so that's how that simplifies. That's how we rationalize the denominator in that case. All right, for fractions that have a square root and two terms, we haven't seen a problem like this yet. So if you have a fraction with a square root in the denominator, so I say for fractions with a square root and two terms, that's in the denominator. If you have two terms in the numerator, it's not a big deal. If you have two terms in the denominator with a square root, either one or two square roots, you have to take a different approach to this kind of problem. It's more difficult to rationalize. What you have to do is multiply by the conjugate to eliminate the square root from the denominator. The conjugate of a plus b is the expression a minus b. So the terms will be the same, except that in one case you're adding, in the other case you're subtracting. That's what makes them conjugates. Same two terms, but you change the sign in the middle. And it's vice versa. The conjugate of a minus b would be a plus b. So when you multiply by the conjugate, what ends up happening is all the square roots will go away. All right, so let's take a look at an example of this type of problem. We have 8 over 5 minus the square root of 6. The conjugate of 5 minus square root of 6 is going to be 5 plus square root of 6. So to rationalize this denominator, you can't just multiply by square root of 6. Let's talk about why that doesn't work. All right, so let's do that over here. If you think, oh, I'll just multiply this by a copy of itself, I'll multiply by a square root of 6. To multiply it to this, you would have to distribute it. And so while multiplying square root of 6 times the square root of 6 does make that square root go away, you would have to also multiply it to the 5. And so it'll just end up over there. And then if you try to multiply by another square root of 6, again, the same thing happens, right? It'll get rid of this one, but then it just shows up on the other term. And so you can't get rid of the square root when there's two terms by just multiplying by a single square root. So that doesn't work. What does work is multiplying by the conjugate. The conjugate of 5 minus square root of 6 is 5 plus square root of 6. So let's see what happens when we multiply those together. So we get 5 minus the square root of 6 times 5 plus the square root of 6. This is what we were looking at in the last video in section 6.4. You're going to FOIL here. So we'll do first, outer, inner, last. 5 times 5 is going to be 25. 5 times positive square root of 6 will be 5 square root of 6. Negative square root of 6 times 5, that's negative times a positive, which will be negative. And then the 5 goes in front of the square root of 6, so we get 5 square root of 6 from that as well. So again, really it's square root of 6 times 5, but we put the number in front of the radical. That's where it's supposed to go. And then we have negative times a positive, which will be negative. And let's use our shortcut here. Square root of 6 times the square root of 6 is just going to be 6. Then you combine like terms, and what happens is you get 25 minus 6, which is 19. Right? So these combine together. But what also happens, and more importantly, are the middle terms cancel out. Right? So I don't know if that grammatically made sense. So what also happens is that the middle terms cancel out. Right? So 5 square root of 6, that's positive 5. Negative 5 square root of 6, those are like terms. Combine them together, they cancel each other out. So we just get 19, which means we got rid of the square root, which means we rationalized the denominator, right? So all of this work I'm doing here, oh gosh, I cannot draw a straight line. Okay, let's try it again. Okay. So all of this work I'm doing here is happening in the denominator, right? So I'm trying to draw that in. And so we end up with we end up with 19 in the denominator. Because that worked, I need to go back and multiply the same thing to the top. So we're going to multiply 5 square root of 6. Sorry, I said the wrong thing. 5 plus square root of 6 to the top. So we're going to get 8 times 5 plus square root of 6. We'll distribute the 8 into the parentheses there. So we get 8 times 5, which is 40, plus 8 times the square root of 6, which will just be 8 square root of 6. These are not like terms, so do not combine that together to get 48. They're not like terms. They don't both have a square root of 6, so you cannot combine them together. You're just going to copy it down. Whoops, and you should do it with the square root there. I don't know what I'm thinking. Okay, so this is what we end up getting. 40 plus 8 square root of 6 over 19. Sometimes you'll get a fraction here that can be reduced. Like you could factor out a common factor, cancel it out with the number on the bottom. But 19 is not going to reduce with anything here. So this is going to be our final answer. So that's how you handle having two terms in the denominator with a square root. You multiply by the conjugate. That's what works. All right. Same thing's going to work here. Even though there's two square roots here, same thing works here. You're going to multiply by the conjugate of this expression because there's two terms, which will be square root of 3 minus square root of 5. So same two terms, just the opposite sign in the middle. So when we multiply these together, what's going to happen? We'll have square root of 3 plus the square root of 5 times the square root of 3 minus the square root of 5. We're going to FOIL. So first, we'll multiply the first two terms together. Square root of 3 times the square root of 3 is just 3. Let's use our shortcut there. You multiply square root to itself. You just get whatever number's inside the square root. We'll multiply the outer terms together. We'll have positive times a negative, which will be negative. Square root of 3 times the square root of 5 is going to be square root of 15. You multiply the inner terms together. We get positive times a positive, which is positive. Square root of 5 times the square root of 3, which again is square root of 15. And then you multiply the last terms together. So positive times a negative is negative. Square root of 5 times the square root of 5, shortcut, is just 5. Combine like terms, the square root of 15s are going to cancel out. You get 3 minus 5, which is going to be negative 2. And again, all of that takes place in the denominator, if I can draw it back in. So there we go. And then this will be, oh, okay, I was doing good up until that one. All right. So, okay, that's not too bad. All right. Because that works, we got to go back and do the same thing to the top. So square root of 3 minus square root of 5 gets multiplied to the top. So we get 2 plus the square root of 5 times square root of 3 minus square root of 5. We'll FOIL again because it's two terms times two terms. So we have to FOIL here as well. So we get 2 times the square root of 3, that's 2 square root of 3. 2 times negative square root of 5, that's positive times a negative, which will be negative. 2 square root of 5. So we'll just write it as we just said it. The inner terms, square root of 5 times the square root of 3 will be square root of 15, because those multiply together into a single radical. And then the last term, square root of 5 times negative square root of 5. It'll be positive times a negative, which is negative. Square root of 5 times the square root of 5 is just 5. Then we try to combine like terms, but this one's kind of a weird one. None of them are like terms. None of them have the same radical, so you can't combine any of these together. So we're just going to copy that over. We'll have 2 square root of 3 minus 2 square root of 5. You can just leave it in this order. There's really not a great order to put all these things in. And nothing reduces here because to reduce, I'd have to be able to factor out a 2 and make it a factor to cancel out with this 2 in the denominator, and there's not a common factor of 2. So this is all we can do with that. And so that would be my final answer, and it's rationalized. I'd like you to note that rationalizing the denominator doesn't necessarily mean simplifying, right? I mean, you could argue that what we got here as an answer is more complicated than what we had as the original problem. So we're not really, our goal here is not to simplify, it is to get rid of square roots or radicals from the denominator. That's what we're trying to accomplish. All right, let's take a look at the last page. So this is the last couple of examples I have. So why don't you guys try to do these problems if you haven't been doing that already. Pause the video. See if you can rationalize these denominators here, and then resume the video to see if you came up with the correct answer. So to rationalize this one, it's a cube root. And so with 10, you could break that down as 2 times 5, but it doesn't really help much because everything's still to the first power. So we might as well just think of this as 10 to the first power. To get rid of that cube root, I need to have 3 powers of 10 here to cancel out the cube root. So I need to have 2 more powers of 10. I already have 1. 2 more is going to give me 3 altogether. 3 powers of 10 will cancel out my cube root for me in regards to that factor. For x, we're already past 3. So we need to go to the next best number that will simplify with a cube root, which is the next number that can be divisible by 3, which will be 6, right? So my goal here is to get x to the 6th power, because that will simplify nicely with the cube root, which means I need 2 more powers of x. And then, so that's what I'll multiply by. It'll need to go inside of a cube root for them to multiply together. And what I'll get when I multiply these together is the cube root. 10 times 10 squared will be 10 to the third power. X to the fourth times x squared will be x to the sixth power. And then I will simplify that by applying the cube root to each of these separately. For the 10, we apply the cube root to the 10. It cancels out that power of 3, and we just get 10 out of it, right? So the cube root cancels out that power of 3. When we apply the cube root to the x, we divide the power by the root. So 6 divided by 3 gives me x squared. And now the cube root's out of my hair, right? For the denominator. So it rationalizes the denominator, which means it works. It does what we need it to do. So we go back here and we do the same thing to the numerator. We'll multiply the cube root of 10 squared. I guess let's do this like we did last time. For the denominator, it made sense to keep it as an exponent so we could track it that way. But for the numerator, it doesn't make sense to really track that exponent because there's not another 10 here for it to combine with. So let's just think of it as 100, right? 10 squared is 100, and then times x squared. So again, we're multiplying the same thing to the top and bottom. Multiply these together, we'll get the cube root of 2 times 100, which will be 200. Y to the fourth power times x squared. I don't know why I wrote it in that order. You could put x squared and then y. Sorry, and I put y squared. Sorry, I don't know what I'm thinking. Okay. Should be y to the fourth power x squared. Right? And again, the order doesn't matter there. What does matter, though, is that you can simplify the y. The 200, that one's kind of hard to tell. But again, with cube roots, it's kind of a short list. Can you get an 8 out of the 200? The answer is no. Can you get a 27 out of the 200? Wait, can you get an 8 out of the 2? Yeah, actually, you can get an 8. I'm sorry. I shouldn't make assumptions. So looking back here, I know that you can get a 4 out of the 100, and then you have a 2. So yeah, there's an 8 there, actually. I just kind of dismissed it out of hand, which I shouldn't do. So my point still stands, which is you need to try to simplify it. Thankfully, I caught myself here before I made a mistake. So we can split the 200 up as 8 and 25, right? Because we can take the cube root of 8. If 8 didn't work, we would try 27. 27 didn't work, we would try 64, right? With y, because there's more than 3 powers of y, we can actually get some y's out of this, right? So we'll put 3 powers of y in the good pile. So this is what we did back in 6.3. We'll have 1 power of y left over that goes in the bad pile. But for x squared, there's not enough there to split up, right? We need at least 3 powers of x to work with. We don't have that many powers of x, so it all goes into the bad pile. We apply the cube root to each of these piles separately. The cube root of 8y to the third power, the cube root of 8 is going to be 2. The cube root of y to the third power is going to be y, right? The cube root cancels out the power of 3. The bad pile just gets copied down, so we get cube root of 25y x squared, or x squared y, whichever order you want to write that in is fine. And then, not only did we have to simplify that cube root, unfortunately, we have to reduce this fraction. Not that there's much to do, but the 2 can cancel out with the 10, and it leaves me with a 5. So my final answer here is y times the cube root of 25y x squared over 5x squared. And that's as much as we can reduce it, because again, you cannot cancel out things inside the square root with things outside the square root. Right? So that is how that one works. So I'm sorry, I had you guys try that problem. If you're watching the video, that one was a little bit more difficult than I was expecting it to be. So I apologize for the level of difficulty on that one. If you figured out to multiply by this, I think that's great. That shows that you are really understanding the material. If you didn't catch that this could be simplified, if you didn't catch that this could be reduced, don't be too hard on yourself. Of course, those are things that you will need to do when you're doing the homework and when you're doing the test. But if you're getting the gist of just rationalizing the denominator, that's really good progress. And you'll get you'll get the rest of the details figured out as you work through some examples. All right, so for here, what you had to do is multiply by the conjugate, right? Which is square root of 5 plus the square root of 3. You're going to FOIL these together, right? So it would be square root of 5 minus square root of 3 times the square root of 5 plus the square root of 3. You'll do FOIL here. So square root of 5 times the square root of 5 is going to be 5. Square root of 5 times the square root of 3 will be positive square root of 15. Negative square root of 3 times the square root of 5 will be negative square root of 15. Really familiar to a problem that we did earlier. And then Negative square root of 3 times the square root of 3 will be negative 3. Right? Negative times a positive will be negative. Square root of 3 times the square root of 3 is just going to be 3. The square root of 15s cancel out. You get 5 minus 3, which is going to be 2. So that's what we get on the bottom. On the top, we're going to multiply by square root of 5 times the square root of 3 as well. But what I'm going to recommend before we distribute, because that's what ultimately is going to have to happen here, before we distribute, if you just copy it down here, we have negative 8 square root of 7 times the square root of 5 plus the square root of 3. Okay, sorry about that. I had to pause my recording because somebody knocked at my door. So I don't know how smooth of a transition that's going to be, but what I was trying to say here was by leaving this out without distributing it first, it's a factor, which means we can use it to cancel out the denominator here because we have 8 as a factor on top. We have 2 on the bottom. Those can be canceled out. So if you distribute the 8, you might miss that, how do you say? You might miss that signal that something can be reduced. I don't know, that's not quite what I wanted to say either, but if you distribute it, you might not catch it, that something could be canceled out. That's what I want to say. All right. And so that leaves me with a 4 up here. Right? And the 2 just actually goes away, so it's not even a fraction anymore. So what we end up with is negative 4 square root of 7 times the square root of 5 plus the square root of 3, which now we can go ahead and distribute since there's nothing to hold back, to hold us back from distributing it. There's nothing else to reduce or cancel out or anything like that. So we'll go ahead and distribute it, and we will get negative 4 square root of 35 minus 4 square root of 21. All right, and then that'll be our final answer here. All right, so that concludes the video for section 6.5 on rationalizing the denominator.